Okay, so why don't we get started? Let me just start with some announcements first. We have finalized the office hours for the semester. Okay, I posted them on Piazza already, and they will also shortly appear on the course webpage. By and large, you can come and expect to see someone each day of the week. So we'll have daily office hours. Most of the weekday office hours will be hybrid. They'll be held in person in the conference room that's actually across the hall from this classroom, just one down there. It's A302. Or you can also join over Zoom and ask questions. Okay, it's up to you. On weekends, they will only be on Zoom because this building is locked on weekends. Okay, so you cannot enter without swipe card access. So we will only have Zoom office hours on it. Okay, so you can use these office hours to come ask questions about either the lecture or as we start handing out lab, if you have programming questions, that's when they are especially helpful. Okay, of course, you can always use Piazza to ask questions. That's never a problem. But if you need personal help, just come see one of us. Right. So office hours are now posted. Just as a quick announcement, today's office hours will be right after class across the hall and also over Zoom. Okay, so if you need to see someone today, you can do that as well. Okay, as the first thing. Second announcement is I am about to give out the first problem set, okay, which is going to cover the first 3 lectures that we've had, which is going to include today's lecture, and it will also have a lablet, okay, in addition to some written questions. Lablets are just way by which you can look at some code and try to understand the concepts at a little more deeper level. Okay, doesn't actually require, lablets don't require you to write code. Okay, lablets are typically meant for just playing with code that we give you, so you just get some understanding of what these concepts mean. Okay, so I'll hand that out later today. Watch out for it. We will put a note on Piazza, and because this is the very first time, I probably will also send out an email just telling you about it. Okay, and then we will continue. We'll start a new topic today, by the way, which is going to be on communication. Okay, as far as the book is concerned, this is actually chapter 4. Okay, we've skipped chapter 3 for now, but in 2 or 3 classes, we'll come back to what the material in chapter 3. Okay, so we've done 1 and 2 is already done. Okay, so I would strongly encourage you to go and look at the class slides, review the relevant section from the Tannenbaum book, which also has good material for what I've covered. But today is really the first major topic for the course. Those 2 lectures are really introductory lectures, the introduction. Okay, but you should still know that material. So today we'll start with chapter number 4, and then we'll come back to chapter 3 in 2 classes. Okay, and the last announcement, which I said last time, which I want to repeat, is we are still looking for scribes to sign up. There has been almost no lectures that have been taken. So there are plenty of slots available. It's not a lot of work. If you agree to be a scribe, you just have to take notes during class. And of course, online students can be scribe as well. You write some notes. We'll give you last year's notes, which are similar. You just update them, send it back, and you get a small bit of points as part of class participation. Not a lot of points, but if you at the end of the semester find yourself at the boundary of some grade, it may just boost you to an upper grade for maybe not a lot of work. So again, I would encourage you to sign up. There is no scribe for today's class yet. There's one for next class who signed up already. Does anybody here want to be a scribe today? Okay, come and see me after class and take some notes. Okay, thank you. All right. So those are the announcements. So let's get started. Okay, I do have one lecture, slide that I did want to cover from last time. So if you remember, last time we were talking about distributed systems architecture. I explained a whole slew of architectures which are used to design distributed systems. We start with layered architecture. We looked at object-oriented. We looked at resource-oriented, also called RESTful architectures. And I talked about client-server architectures. in which we looked at multi-tier ways of building an application. Towards the end, we were talking about peer-to-peer or P2P architecture. Okay, so one slide that I did want to cover from last time, which is a type of peer-to-peer system that is quite popular, is BitTorrent. Okay, probably you've heard about BitTorrent or used it to download some large files. So this is just a slide that explains how the BitTorrent architecture works. And so BitTorrent is essentially, think of it as a way to collaborate on downloads of large files using multiple peers. Okay? One of the interesting aspects of BitTorrent is it lets you do parallel download. Okay? You try to download a file, let's say from a website over HTTP, you just have one connection, you're downloading a large file, it may take a while. Okay? When you use a system like BitTorrent, what it can do is it can connect to multiple other peers and try to download different parts of the file in parallel. So it parallelizes the download, which can speed up your download. Okay? So the way things work in BitTorrent is you are given a large file, you partition it into smaller pieces called chunks. Okay? Chunks are then distributed across peers. So each peer may have one or more chunks. And when a peer wants to download those chunks, it has to get them from the peers that have them. Okay? But it doesn't have to get them sequentially. You don't have to say get chunk 1 from this peer, and once it's done, go get chunk 2 from this peer, and so on. You can actually connect to K peers in parallel and say, let's get the first K chunks, and then let's get the next K chunks. Okay? That might speed things up. If you have a good network connection, you can make better use of the bandwidth on your machine and speed up the download using parallel transfer. Okay? And then once you've gotten all the chunks, you got to reassemble the files by just piecing the chunks together. Okay? Now, that's the basic idea, but how does it actually work? Yeah, so essentially, there's a picture here that gives you some example of a BitTorrent system. So the way you want to think about it is there are 2 or 3 parts to BitTorrent. The first one is called a torrent file. Okay? Think of a torrent file as having some sort of information. It's an actual file that you got to download from somewhere in order to download this large file. Okay? So to get a file, first you got to get a torrent for that file. Okay? Torrent could be posted on a web page, or it could be posted somewhere else. Somebody can send it to you and so on. Okay? So the torrent file essentially maintains a bunch of information about how to get the file. The first thing it tells you is something called a tracker. Okay? A tracker is essentially a server machine that tracks all the active peers that are in the system that are requested chunk. Okay? So here's a picture. So there's a client node which is circled at the top. You go to a website and you get a torrent for downloading that file. Okay? The torrent file is essentially going to, which is this file, is going to refer you to a tracker. The tracker is going to track all the nodes that are currently up and have some copy of the file. Tracker essentially says, here's a server. It says there are 10 peers that are up and they have different parts of the file, and the tracker will tell your client, saying, if you want to download the file, here are the n peers that have some chunks of the file. And then your client has to connect to those peers and start getting files. And you can decide what K is, which is how many chunks do you get in parallel. That is up to the BitTorrent client. You can decide that based on how much network bandwidth you have and so on. Okay? Now, one interesting thing that you have in BitTorrent is this notion of altruism, which says that you cannot just simply download content from other peers. Okay? You also have to share the content you already downloaded with others. Okay? So if you're acting as a selfish user that simply downloads the file and then shuts down BitTorrent and does your work, and then next time you go and try to download another file, BitTorrent will explicitly slow you down. Okay? To get fast downloads, you have to actually participate in the system. And so that means that you can't just use other peers' resources. You also have to contribute back to the system. Okay? This is called altruism, the term that is used in other contexts in distributed systems. So it is forcing altruism by giving an incentive to be part of the system, okay? Which means that you got to also share resources, which is your disk and chunks that you're downloaded with others, not just download from. Okay? So that was a problem in peer-to-peer systems where a large number of users were essentially freeloaders. They were consuming resources from the system but never contributing back. And they explicitly added that incentive back into the system. So if a peer sees another peer that has done more download than upload, you will reduce the sending rate. You will just send your chunk to that peer at a slower rate, which means that it will take it longer to download. So that's an incentive mechanism that's explicitly built into BitTorrent. Right? Yes, question there. Okay. Question is BitTorrent a protocol or a client or a system? It's actually both. BitTorrent is a protocol in that it tells you how you can initiate that process. What does a torrent file contains? What does a tracker contain? What is the protocol that you use to connect to a peer to download it and so on? Okay? Now you are saying you could change the code and remove the altruism, but remember that the altruism is forced by the other party. If you are selfish, the other parties are reducing its sending rate. Not that your client is downloading at a slower rate. Your client is your own, okay? But others will send to you at a lower rate based on how much you participate. So you can't change somebody else's peer. Okay? So you can, of course, change your client, but that doesn't help in this case. All right. Okay. So let's now switch gears and actually start today's topic, which is going to be communication in distributed systems. Okay. So today what we have are essentially a quick introduction to networking basics. Okay. Generally, you should have known this some of the networking concepts in some sort of an undergrad class, whether it's operating systems or networking and so on. And just in case you don't or you've forgotten, I'm just going to go through very quickly in 3-4 slides some very basic concepts about network. Okay. And then what I'm going to show you is how can you use those networking concepts to implement message-oriented communication. Okay? Typically, everything we have seen last time, okay? Whether it's client-server, whether it's peer-to-peer, whether it is layered architectures, object-oriented architecture, all of these components are software and processes that run on multiple machines that communicate with one another. Okay? The question is, how does that communication happen? Okay? In today's class and next time, we'll actually see how to implement all of that communication. So you can write applications where these two pieces run on two different machines and yet they can communicate. Okay? So we'll see the basics of message-oriented communication using some low-level protocol, low-level concepts such as socket communication. Okay? Then we'll talk about a bit higher-level construct for inter-process communication, which is called remote procedure calls or RPCs. Okay? And then next time, not today, we'll actually talk about another way to do this called remote method invocation or RMI. But for the rest of today's class, after I introduce RPCs, we'll look at some implementation issues. Okay? And the first problem set that I'm going to give out today actually gives you sample code that explains all of this concept using tiny snippets that you have to actually run an experiment with so you get a better understanding. Okay? And the reason you have to do that is the lab that is going to come next is actually going to require you to implement this, okay? Because you will write some sort of a client-server application, so you'll have to implement this. So we are going to give you some sample code so you get some familiarity with these concepts, because the assumption is you have not done something like this before. Okay, so today we'll do those first three parts, then RMIs, which is how do you do Java, RPCs in a Java world, is next time. Right. So let's start with some very basic concepts. Okay? So there are two ways processes can communicate with one another. Okay? One is called unstructured, and the other is called structured communication. Okay? In unstructured communication, you essentially use shared memory or buffers to communicate. Okay? You want process A wants to communicate with process B. It can write some data to a shared buffer, and then process B can then go and look in that shared buffer and pick whatever data was written by process A. Okay? That is called unstructured communication. And needless to say, this unstructured communication works much better when process A and B are on the same machine, because this buffer is a piece of memory that resides on that machine. If both A and B have to access it, and it has the A and B have to run on the same machine. Okay? Unless you have a way to share a memory region across machines, which we haven't looked at. That's called distributed shared memory. We haven't talked about it. For now, memory is resident on a single machine. Yes, question. Okay. All right. So now that's a good question from operating system. If you remember your OS class, you'll remember that there's a process abstraction. Okay. Processes are allocated memory and specifically virtual memory, and virtual memory is isolated. One process cannot actually access another process's memory. Okay. So whatever I just said here is exactly the opposite of what you must have studied in undergraduate. Okay. Now let me explain how this works. So the operating systems, and you probably did not study this in an undergrad OS class, have a special concept called shared memory. Okay. So when you create a process, you get virtual memory. That's not shared. That is exclusive to you. Only you can access it as a process. No other process can access it. But that process can explicitly go to the OS and say create a shared memory region. Okay. A shared memory region is actually a memory page that is designed for sharing across processes. Okay. So you have to create this shared memory segment. It's called a segment. It's a region. Just as you malloc or use new to allocate memory, you will allocate a special type of memory called shared memory, and then you can have another process access. Okay. So that's how you would do it. Not something you would normally learn in an undergrad class, but that's essentially why you are now in a grad class, to learn about more advanced concepts. Okay. So you will shared memory or you will need shared data structure, but nevertheless, that's still single machine abstraction. Okay. How do processes across machines communicate? They have to use what's called structured communication, where they pass messages back and forth. Okay. A message is essentially nothing but a piece of memory that you say, I will put some data into that message, and you will tell the operating system, send this message to this other process on some other machine, and the OS is going to send it, and then the other process is going to get that message, and whatever came in the message, it can then act on it. Okay. So you have this abstraction of a message that is sent back and forth. Okay. That is how processes will communicate. Now, this is called inter-process communication, or IPC. The term here is essentially inter-process communication. And this works regardless of whether the two processes A and B are on the same machine or across machine. You can still use messages to communicate between these two processes. Okay. So there are multiple ways we can achieve this. We'll look at two today. Okay. One is a low-level method for inter-process communication that uses what is called socket-based message passing. It uses the concept of network sockets for passing messages back and forth. And then we'll see a higher-level construct for IPC, which are called remote procedure calls. Okay. So we look at both. Okay. Now, as distributed systems, you will need essentially both low-level communication, high-level communication. You will try to construct applications of different types. So we can use either of these depending on your needs. Okay. They will achieve the same goal, which allow processes in a distributed system to communicate. And you can have more than two processes, by the way. In this example, I said only two, but you can have more than two. You can still use IPC for communication. Okay. Now, before we talk about sockets, a very quick basic recap of communication protocols, okay, which you probably should have some familiarity with. So this figure here essentially shows what is called a network protocol stack. Okay. All networking protocols essentially are arranged in a layered fashion, which is actually showed here. So you see these boxes, they are stacked one on top of the other. That uses a layered architecture that we talked about last time. Okay. The TCP/IP protocol stack is an example of this. This is called the OSI protocol stack because it essentially has 7 canonical layers. Okay. The lowest layer is called the physical layer. That's essentially how you can communicate over a physical medium, such as a wire, or how you communicate over a wireless channel. And then you have something called a data link layer, network transport session, presentation, and application layer. But before I go into some of these details, let me explain what is a protocol. Okay. Protocols are rules for communication. Okay. Protocols are rules because if you have two parties that are communicating with one another, they have to essentially speak the same language. They need to understand if some message comes from the other end, how do you interpret that message? And protocol essentially defines the rule that allows you to interpret whatever is coming from the other end. Okay. And in a protocol stack, there are different layers and they serve different purposes. Each layer is essentially implementing one protocol. Okay. And it serves a specific purpose. Okay. And you have two machines in this example, machine A, which is the protocol stack shown on your left, and machine B, which is the protocol stack shown on your right. Okay? Both of these machines are going to run this protocol stack, and then the application uses the protocol stack to send messages back and forth. Okay? And by and large, what is happening here is that the applications are at the top. Application will construct a message, and then it's going to ask the OS to send the message. The message is going to traverse down the protocol stack on the sending machine. Each of these layers is going to process that message and send it to the layer below it. So it'll go all the way down until it hits the physical layer, and it goes out on either the wire or on a wireless channel. It appears at the other end, and then the message gets processed in the reverse order. It traverses up the protocol stack. Again, the message undergoes some processing at each layer of the protocol stack, and then the receiving application just sitting at the top here is going to receive the message. Okay? That's how a network protocol stack is going to work. Okay? Now, there are these different layers. I'm going to very quickly mention them. Physical layer essentially is a set of rules that allow the computer to send messages either on a wireless channel like Wi-Fi or on a wire such as Ethernet. It basically says, how are you constructing the packet? How do you transmit it over a wire or on a wireless channel and so on? So that's your physical layer protocol. The data link layer essentially is either it's called Ethernet protocol or it's essentially MAC layer protocol. What this does is it ensures that when you send a message, it is successfully received at the other end. It does not incur what are called collisions where two computers are trying to send at the same time. Okay? In which case, those messages are going to incur what's called a collision. They'll collide and they'll get garbled. Only one machine can send at a time because this is a network is a shared medium. Okay? The link is essentially a shared medium. So only one can send at a time. Okay? So that is handled at the data link layer protocol. The network protocol is essentially responsible for routing. Okay? In the TCP/IP world, that's where IP resides. IP stands for Internet Protocol. And if you are sending a message from machine A to machine B, there may be many other intermediary machines called routers in between. And the routers are essentially going to perform a task called routing, which is what's the next machine to send this message to. It goes one hop at a time until it gets to the destination. Okay? So routing is performed by the network layer. Transport layer does what is called end-to-end control. It decides what is the rate at which I can send. Can I send packets at a fast rate? Should they be sent at a slow rate? That depends on the state of the network. If packets are lost, you can use something like TCP in this case to reconstruct lost messages or retransmit rather lost messages and so on. Okay? Session layer and presentation layer are designed for session level protocols and presentation. In the TCP/IP protocol stack, they're actually absent. Okay? You only have the transport protocol, and above the transport protocol is your application. Okay? Now, in case of application, if you have a web browser and a web client, your application here is a web browser, there it's a web client. They are using the HTTP protocol, which I mentioned briefly last time. Okay, that's an example of a protocol stack. I'm assuming you know this, but this is like a 2-minute summary of what you should know so that whatever I talk about next makes sense. Any questions here before I can move on? Yes, any questions? Okay. All right. So that's the protocol stack. Here is the structure of a message that is actually sent from the sender to a recipient. So the sender, let's say it's a web browser, okay, is going to construct a message. Let's say it's trying to get a page or something like that. So that message, that HTTP message is going to be here. Okay? That message itself will have a HTTP header and HTTP body, and then you will hand it down the protocol stack. And each layer of the protocol stack is going to add its own header to that message. Okay? So if you have TCP, you will have a TCP header. If you have IP will add another header. So that by the time that message, and then if you are sending it over Ethernet, you will add an Ethernet header and so on. So when the packet is actually going out or this data is going out on the wire, it has multiple headers that have been attached to the message. In particular, you will have an HTTP header, TCP header, IP header, and an Ethernet frame header. Okay? And that message is going to go to the other end at each when it's received. Then you do the processing in the other direction. So the Ethernet layer, which is the data link layer, is going to look at the Ethernet header and say, what do I do with this message? That's all the information, but what to do is in the header. Okay? They will strip that header and send it off to IP. Okay? And IP is going to look at IP header saying, what should I do? And then they'll hand it to TCP. We'll look at the TCP header, we'll strip it off and then and it in this case to HTTP and so on. So you will start stripping these headers off, and then when you get back to the application, you're left with the messaging, okay, which is what was sent by the other end. Because everything else was just done for sending the message over the network, not required by the application itself. Is this clear? Okay. So that's just layered protocols. Very quickly, we will talk about middleware systems later on in this class. Okay, what they do is they inject a layer between the transport protocol and the application protocol. Remember that I said in TCP/IP, we don't have the presentation layer and session layer, so those are not there. So the application would typically sit directly on top of the transport layer. Application directly talks to TCP/IP, or rather TCP in this case. But when you add middleware systems, you will have a middleware layer that will sit between the application and the and in this case the transport layer, and it will provide some higher level functionality to the application, which makes it easier for the application to communicate. Okay? We'll see a variety of middleware system later on in this course, but one example of a middleware protocol would be how to do distributed commit, or how do you do things like distributed consensus, Paxos. There are all kinds of protocols we'll encounter. The way you think about them from this perspective is that they sit between the network protocol stack, which is transport layer and down, and the application which sits at the top. So it'll be a layer that sits in between them. All right. So that's all I'm going to say about middleware now, because we'll come back to it at a later point. Okay? So with that background, let's now talk about how do you do this message passing I was describing a few slides earlier. Okay? So the most basic level of message passing is to use what is called socket-based communication. Okay? So first thing is, what is a socket? Okay? Think of a socket as a network endpoint. Okay? It's essentially within your network, you create an endpoint that allows some process to send you messages. So it's almost like an address that you are going to use to receive messages or send messages. Okay? So you have to, in order to construct two processes, let's say they're client and a server that want to communicate, you first have to establish a connection between the client and the server, okay, or these two processes. In this case, it's going to be a TCP/IP connection, because we assume that TCP/IP is basically the protocol that we are going to use. Okay? And the way you create a TCP/IP connection is that you are going to create one socket on each end. You'll create a socket on the client or process A. You'll create a socket on the server and process B, and then you are going to connect them together. When you connect them together, you establish a connection between the two endpoints, one at the client, one at the server. Okay? And then you can use this connection to send any data back and forth of your choice. Okay? Now, this is going to require you to use all of these primitives, okay, which I'm going to show you pictorially: socket, bind, listen, accept, connect, send, receive, and whatnot. It's not important right now to read this table. What is important is to understand this figure. Okay? So this figure essentially shows you how to write a very simple client and a very simple server that communicate with one another using sockets. Okay? So you will see that, and so this is essentially the x-axis is time. So each of these components has to make those specific calls that are shown in the boxes for communication to take place. Okay? So the client has to create a socket, and socket says, I just need an abstraction or an endpoint that I can use to communicate with another process. Just as you have a file handle, when you open a file, you get a file handle or a file pointer. When you open a network connection, you get a socket handle that you are going to use to send or receive data. Okay, so the client will call the socket call, create a socket. The server will call a socket call, create a socket. But then the server has to do additional things. The server has to assign a number to the socket. Okay, all sockets have unique numbers. Okay? The server has to say, this is essentially the number I assign to this socket. That's the address at which the server is going to listen. Okay? So you pick a unique number that maybe no other servers running on the machine are used. So you pick that number, and then you say, I'm going to start listening at that address for any data that's coming to me. Okay? You call the listen call. Okay? And then you call something like called accept, which is going to actually create a connection to whoever is trying to connect to you. Okay? So essentially, this client is just going to open the socket and say connect to that server. Okay? The server has to create the socket, assign an address to it, start listening on the socket and say accept. When you do accept at the server and connect at the client, you will actually establish a TCP/IP connection between the client and the server. Okay? So this is where you have the client has connected to the server. Once you're connected to the server, you can then send or receive data or read or write data. Okay? Just as you read or write to a file, you can take the socket handle and write to it, which means you'll send data, or you can use explicitly the send call to send any data to the server, and the server can receive data, process it, send back a response, and so on. So you will see there are multiple loops here where the server has read something from the client, processed it, sent back a response. So the read is read, or analogously, you can basically do receive. You can receive data, or you can do write or send. And here also you do the same thing. So you have multiple communication messages that go back and forth. So this is the actual act of sending a message and receiving that message. Okay? So you have to do all of that extra work for you to actually send that message to the server. And the server has to do the same to receive the message. And once you're finished with your communication, you can close the socket, and that connection that you had established is now shut down. Is this clear? Okay. So now I'm going to show you some actual code. This is actually going to be part of your lablet as well, because you have to write this code, or in this case, we'll give you this code. You can play with this code. Okay, so you'll see whatever I showed you as pictures is represented in this code. Okay, the client code is the top green box. The server code is the bottom green box. This is Python code, a similar Java code that you can write if you want. Okay, so you will see at the client, you call the socket call. Okay, that creates your socket, and you get back a handle called S. And then there are some arguments here which we can ignore for the moment. Those are default argument to create a TCP socket. You can also create what's called a UDP socket, which you will not really use in this course. So you don't have to worry about what those arguments mean. Okay? And then this socket is going to essentially connect on address 80. Okay? Because this is, let's say, a trivial web server. Okay? If you are writing a web server, all web servers by default listen on what's called network port 80. Port number is essentially the socket ID. Okay? So to connect a web server on a machine, you have to connect to socket number 80 on that machine, because I told you sockets are numbered. Okay? That number is the address of that socket on that machine. Okay? Now, well-known services like SSH, HTTP, FTP, they listen on well-known addresses. So if you want to connect to that service on that machine, you already know the address of socket address of where to connect. Okay? You need the IP address as well. That's different. Okay? The IP address is the address of the machine. The socket number is the socket number on that machine at that IP address. Okay? So here you said python.org. That's essentially a domain name which will translate to an IP address. So you're connecting there, and you listen on port number 80. Okay? If you have SSH, that listens on port 22. If you have some other service that's well known, you can listen on those services. If you are creating a random application, you get to pick a port number. Okay? And you can decide whatever port number you want. It's just that you cannot pick what are called reserved port. Reserved port numbers are reserved for well-known services. So you can't write some random client server application and make it listen on port 80 unless there's actually an HTTP server. So because that's what's supposed to listen on port 80. Okay? So that's the client. Here's your server. Okay? So here you're connecting to that server on port 80. So that's the IP address, that's the port number. Okay? Here is the server. The server created a socket. Okay? Then, as I said, you have to bind that socket, which means that you have to say this socket is going to connect to port number 80 on that machine. Okay? And then you listen, saying that now that the socket has been created, I'm going to start listening for messages that are coming to port 80 on this machine. And then you are going to essentially sit in a loop and do accept, which means that you're accepting connections. Okay? Exactly what I showed you on this previous slide. Yeah, so you have a socket, bind, listen, accept. Okay? You will see that same sequence in the code here. Okay? So once you do this, now the client can communicate with the server and start sending. So the act of actually sending data is not shown in this code. You only connected, but then after this, you can write to the socket, which means you'll send a message. And here you can do receive from the socket, which means you can receive the message and they are bi-directional connections. Okay, so a client can send a message to the server can send a message back to the client. All TCP/IP connections are bi-directional. Is this clear? This is basically a very trivial skeleton of a client-server application. Okay? And you have to write all of this code for this application to listen on sockets. And if you want to connect to multiple machines, for each machine, you'll have to create a socket connection and establish a connection to that machine. Okay, any questions here? Yes. Sorry, what's the question? Server socket dot listen. I think that's what is 5. Yes, I think it's some sort of a timing primitive, but I'll get back to you. I actually forgot what it means in the Python word. Okay. Okay. Anything else? All right. So let's look at under the hoods how TCP is actually doing things. Right? So we just did this at a higher level. Okay? We didn't actually understand what TCP does to establish this connection. Okay? So when you essentially do a connect and an accept, what does TCP do to actually establish the connection between the client and the server? And you basically have this figure on the which is labeled A that tells you underneath, okay, how is TCP establishing a bidirectional connection between machine A and machine B. Okay? This uses what is called a three-way handshake protocol that is used, and you will see why it's called a three-way handshake, because these are all the messages that are actually going back and forth between the machines for communication to be established or the connection to be established. Okay? So the client, in order to connect to the server, is going to call what is called a SYN message. SYN says, essentially it says, I want to establish a connection. It's called a synchronized message, but the intent of a SYN message is, I would like to establish a connection. Okay? And then the server, because this is bidirectional, is going to send a SYN in the reverse direction. Okay? Because saying, I would like to establish a connection in the reverse direction. Okay? And TCP also acknowledges every message. So for every message you receive, you have to send an ACK so that the other end knows your message was received. If you don't get an ACK, the other end will time out and retransmit the message. Okay? So you will see that there is a SYN and there's an ACK for the SYN that came from the client that goes back. Okay? And then the client is going to ACK the SYN that the server sent. So there's an ACK that goes back in the other direction. Okay? After these three messages are exchanged, the client and the server are agreed to establish a connection, because the client told the server, I would like to establish a connection. The server told the client, I would like to establish a connection, and then everything got acknowledged. Okay? But it requires three messages. Okay? So you have a SYN coming back and an ACK for the SYN to go back. This is why it's called a three-way handshake. There are three messages that go back and forth before the connection is established. Okay? Once that connection is established, then the client and server are free to send whatever messages they want. Okay? In this case, in this example, we assume that the client sends a single request to the server. Okay? It just wants to send a request and get a reply. That's all we are trying to do here. But you can send as many as you want, because the connection is going to stay open until you're done with it. Okay? So you're going to send a request message. Okay? And since the client is only sending a request, it can say, I am done. Okay? And so I start even tearing down the connection in the forward path by sending a FIN. FIN says, I'm done sending this. Okay? So what is going to come back from the server is an ACK for the request and the FIN. So those two messages get acknowledged. You send an ACK, okay, so that the client knows they're sent. And then it'll send the answer at some point after it's done processing the request. And then it'll say, I am done as well by sending a FIN and then an ACK to them. So the teardown is also a three-way handshake. You send FINs in both directions and you do acknowledge, and then you send an ACK. Okay? So what this is telling you is, for simply sending one request from the client to the server and getting back one response back from the server, you essentially sent 9 messages. Okay, so you'll see that there are actually 9 messages that are going back and forth. But that's how TCP works. That's the overhead of using TCP. Okay? Only two useful messages from the client and server's perspective was the request and the response. All of the rest is protocol overhead messages. That's what the protocol is doing, just to set up the connection, tear it down, acknowledge messages and what. Okay. So there have been efforts to try to reduce that number. Here's an example of a protocol which looks like TCP, which tries to say, let's not send 9 messages. Let's try to batch messages and reduce the overhead. So in this case, you can say, I'll send the send message, I'll put the request, I'll say I'm done, all in one message and send it off. Say, I want to establish a connection. Here's the request I want to send, I'm done sending. Yeah. So this goes, those 3 messages here go as one network message. Okay. And then the server is going to send 4 things back as one single message. It'll include a send. It'll say here, I would like to establish a connection. I acknowledge everything you sent so far. Here's the answer, and I'm done. Okay? That goes as one network message, and an ACK comes back saying, I received everything. Okay? So this can collapse that overhead to 3 messages. Okay? Just a proposed variant of TCP, which never got implemented, but just to tell you that people did think about how to reduce the overhead of this message exchange. Okay? For single request, single response, this is a high overhead. If there are lots of communication between the client and the server, these extra 8 or 7 messages don't matter, because you might say 1,000 other messages between the client and the server, then this overhead is very low. Okay? But in most cases, when you have web browsers and so on, you might be sending one request, getting a response, then you tear down the connection. For that, you pay an extra price here as part of TCP. Yes, question? Yes. Tear down the connection is similar to closing the file, so you can no longer read or write to it. So here, tear down the connection. What you would do in the code is you will just call close that socket, just as you close a file. Okay? When you call close, internally TCP will send a fin message. Okay? So tell the other end saying the connection has been closed by the user. Okay? And so that will indeed break the read-write loop and say, I'm done sending. In this case, there was no loop. You just send one request, got a response. But normally, you would have more messages going back. Okay, yes, question. Is there a reason this didn't get implemented? So to implement any change to any network protocol, okay, every computer in the world has to change its implementation. So you can't have one machine talking this version of TCP and the other machine talking that, because protocols are agreed by both ends, right? So rolling out any change to TCP/IP is very hard, because there are hundreds of millions of machines. They would all have to be upgraded. Okay? So it's very hard to do anything at all with TCP. Once it's out there, you just have to live with it. So you can't actually roll it out. Now, in some limited context, you might be able to write your own library to do something, but not for standard TCP. Any other questions? Yes. Okay, what is the drawback of the second implementation, which has any messages back? There is no drawback per se, other than it's not easy to roll it out, actually deploy it in the real world, because it is trying to improve the performance of TCP when you have short message exchange, just one request, one response. Okay, and so you reduce the overhead. But it's, as I was saying, deployment is the actual challenge here. There's no performance issue. Performance actually will be better in this case. Okay. All right. So let me talk about a few other things, and then we'll talk about RPCs, which will try to do the same thing. We'll implement a client and a server with RPCs, but you'll see that what you do as a programmer is very different than what you do when you try to write socket-based application. Okay? But before we do that, let's talk about group communication. Okay? So far, what we have talked about between the client and the server was one-to-one communication. 2 processes is a pair that talk to one another. Okay? So you essentially have pairwise communication. But you might say, what if there is a machine that wants to send a message to n different recipients? Okay? So in this case, if you are using standard TCP/IP, you would have to open n sockets. and send that message n times. That's the only way it will work with TCP. Right? If you want to send the same message to n parties, then you will have to open n socket connections, and you need bidirectional pairwise connection, and then send the same message to your client 1 and client 2 and client 3, client 4, and so on. Okay? And as the group size grows, that can become wasteful. Okay? So as a result, networking technologies will allow you other abstractions which are called group communication, where you send once to a group, and all machines that have subscribed to that group are going to get that message. Okay? The best way to understand this is think about email and use of mailing lists. Okay? When you send an email, that's one-to-one. You have one person's email you put, and you send a message, it goes to that entity. Okay? But if you want to send a message to n entities, okay, as a user, you might actually specify n addresses, but internally your system has to send n messages, one to each of the recipients. Okay? But if you just have a mailing list, you just have one address you send to, and then the system takes care of delivering that message somehow, hopefully more efficiently than sending n messages. Okay? So that's called group communication. So it's one-to-many communication is useful in distributed applications. Let's say you want to send a message to all entities, all machines in a distributed system. Instead of sending n messages, you send it once and all of them receive it as part of group communication. So there will be many scenarios where this will be useful. Okay? So now there are many issues here, which we won't look at today. We'll come back to this sometime later. One is group characteristics. Is your group static or dynamic? Okay? Can the machines in a group keep changing, or you construct it once and then it stays static for the duration of the application's lifetime? Okay? Depending on which of the two it is, you might need different methods by which the protocol needs to know when you send a message to a group who to deliver it to. Okay? Can the group addressing, how do you address a group? Okay? Typically, although I didn't say this in socket communication, the client and server need to know each other's IP addresses. By the way. Otherwise, you can't communicate with a machine if you don't know it, or a process on a machine if you don't know its IP address. Okay? Typically, socket communication needs two things. Okay? You need the IP address of the machine, and you need the socket port number, which is the address of the socket on that machine. So this is called a pair, which is the IP address and a socket port number. Okay? So you will need to know these things to communicate. But now if you are addressing a group, how do you decide what to write? So to do this, there are special IP addresses that are group addresses. So typically, an IP address is a unique address of a machine somewhere on your network. Okay? Now, there are some reserved addresses that are meant for group communication. They look like standard IP addresses, but they are in a range of IP which says this is a group address, and then you will have machines that are subscribed to that group addresses that are part of that. So you will use those group addresses, and this type of group communication is referred to as multicast. Okay? You're sending to multiple parties, which is why it's called multicast. Okay? Now, multicast is different from something called broadcast, which you may have heard about in the context of, let's say, local area networks and so on. Okay? Broadcast means send this message to every machine on this network. Okay? That's what broadcast means. Multicast means send this message to this group, which is some subset of the machines on it. Okay? Broadcast is much simpler. And there's a special address for broadcast, which is 255.255. something. If you send a packet to that message, it goes to all the machines on the network. So it floods the network and it goes to all the machines. Now, broadcast typically works only on a local area network. You can't do broadcast on the internet. That's not going to scale. You can't send a message to 100 million hosts. Okay? That won't work. But on a local area network, like if you have an Ethernet network, or at home you have a Wi-Fi network, you can do broadcast, and only machines on your Wi-Fi network or Ethernet will receive that message. That's fine. Okay? But on the internet, you can only do multicast. Broadcast is not allowed because it doesn't scale. Okay? So this is only a LAN-based approach. On a wide area network or an internet, you only do multicast. And there's something called application level multicast, which is essentially emulating multicast using unicast messages. Okay? Because not all networks actually support multicast. It again requires changes to the router where IP actually has multicast capabilities. And not all machines may have implemented that capability. So if you want to do multicast regardless of whether the underlying networking hardware supports it or not. You have to do things at the application level, which is called application level multicast. So this is basically a library that's going to implement multicast as unicast messages underneath. Okay? The user will send one message. User in this case is the application, not the human user. Okay? The application will send one message to a group, and the library will then send n unicast messages, thereby emulating multicast to the application. Okay? So the application doesn't have to send n messages. You put it into a library, which is called application level. And that's another approach to doing this. There are many other issues which doesn't make sense to talk about now, such as atomicity, message ordering, scalability. We will come back to this later on in this class when we talk about other aspects that require multicast, where we'll try to understand what atomicity means, why ordering matters, and things of that. Okay? For now, all you need to know is a network supports a primitive that allows group communication. Okay? From an application's perspective, you send once, and that message goes to n different machines or processes that are part of the group. Okay? And that's different from unicast. Unicast means one-to-one. Okay? Essentially, all the socket stuff we talked about, that's unicast messages. Okay? So by default, most of what you will do will be unicast. Okay? Because you'll write a client and a server, or two processes that talk to one another, or two peers. They're just two machines communicating with one another. Group communication is a special case. Most likely you won't write code in this class for group communication. Okay? Any questions here? All right. So that is end of part 1. I'm going to now switch to remote procedure calls and talk about a different way of message passing. Okay? Now, what is remote procedure calls? Why is it important for you to understand it? So let's start with some motivation. Okay? So as you perhaps saw, when I showed you socket-based code, okay, it's not easy to write applications that communicate, because you would write all this other code about the networking aspects of it. Okay, I didn't even show you what the application does. All of that code was simply to establish connections, and you as the programmer have to write all of that code for your two processes to communicate with one another. So you could say, can I have higher level abstractions that don't require me to write such complex code, or hide some of that from the programmer? Okay? So RPCs are one such abstraction. Okay? The goal of remote procedure call, or RPCs, is to make distributed computation look like centralized computation. So the goal here is, why not take some abstraction that you already know? Okay? Because you have written other types of code, and we can reuse that abstraction to enable network communication. In this case, it may be much easier for you to write code, because you are not learning new concepts. You are using existing concepts you already know to essentially write distributed applications. Okay? That's the goal. Now you can say, what is this abstraction that I know that I can use to write clients and servers? Okay? The simplest abstraction you can think of when you write code is that of a function or a procedure. You know how to write functions. You know how to call functions from other functions. Okay? Can we use this abstraction to enable distributed application? Okay? And that's the basic idea behind remote procedure calls. The idea is, when you want to send a message to another machine, you're not going to send an actual message. Instead, you are just going to call a function, which you already know how to do, because you've written code that writes function and calls function. Okay? Now, it just so happens that the code for this function is not going to reside in this process that's making the call. It's going to reside in another process running on some other machine. Okay? So you as a programmer just make a function call. Okay? The underlying system realizes that the code for this function, this is not a local procedure, this is a remote procedure. So to invoke this function, the system is going to send a message for you. Okay? That's going to go over the network, go to the other end. And then the other end is going to look at this function and say, okay, this has come over the network. It's going to execute the code for this function, just as you call a local function. Okay? And maybe the function is going to return some return value. Okay? That return value will come back as a message. Okay? And that function call you called is just going to return with that return value. Okay? So you just called a function, and all of the things happened underneath the hoods, which means that you sent a message, not you as the programmer didn't write any code. Your system sent a message went over the network, code got executed, you got a return. Okay? So if you write your applications this way, all you're writing are essentially functions and code that involves functions. In some case, the code is local, so these are local procedures. In some case, the code resides on another machine, the remote procedures, and you just call functions as if they are any function, and your system takes care of figuring out, is this a local procedure? Then call the code that's in this process, which you wrote. It's a remote procedure, send a message, execute the remote procedure, send back a return. Okay? So that's the basic idea behind remote procedure call. So we'll see how it works, and then we'll talk about lots of implementation issues. So here's a picture that explains exactly what I just said. Okay? There are two boxes here. There's a server process, there's a client process. The server process is going to implement a function called add, going to take two arguments, is going to sum them up and return a value. Okay? That's our remote procedure. It's the add function. Okay? So it's going to sit on this machine, the code for the add function. Okay? Here's the client process. Okay? The client process to send a message to the server or to invoke the add function, it's simply going to, in the code, just call add I, j, just as if you are calling a local function, local procedure. Okay? So you just call the add function. Okay? There is no mention of, is this on the network? Where is the server? What's the IP address? What's the port number? You are not going to say any of that. You're just going to call that code. Okay? Now, underneath, what is going to happen is that function is going to call something inside that's going to call the RPC runtime, which is going to say, okay, that's a remote procedure. Okay? To invoke this procedure, you must now send a message to the server saying this client wishes to invoke the add function. Here are the arguments it wishes to pass to the add function, send I and j. Okay? And by the way, you need to also figure out what is the IP address of that server, what's the port number. None of that was specified by the user. But underneath, this is all going to use TCP/IP. So you still have to figure out what all of that is. But the runtime system or the library will take care of for you. Okay? You don't write that code as a program. Okay? So the system does all of that and hides it from you. So you just code at a higher level abstraction. So you will see that it constructed this message. It says, here's the procedure. Here are two values. That entire message went over a network. It arrived at the other end. The other end processes it, say, here's an invocation of add. At this point, you will actually invoke the add function. We'll call the implementation of add. We'll pass the argument, you'll execute, generate a return value. You'll construct another message not shown here. And then that message will come back. And then eventually the add function will return with the return value. And then K will have the sum of I and j. Okay? So what this has now done is basically it's taken some abstraction that you are familiar with, which are procedure calls, and said, let's use procedure calls and use them to write distributed applications. And then the compilers and the libraries will take care of all the extra work you have to do, which is establishing that socket connection. All of that is still happening by the way. Okay? But it's happening in a library, so you don't write the code. You write socket code, you have to write everything. Okay? Use RPCs, RPC system does it for you. You just write a code at a higher level. Okay? So now this is a much easier to understand client-server application, because from your perspective, you just write the code for the function and put it at the server. You invoke all that code from whatever client you want, and then all the other things are taken care of. Okay? Is that clear? All right. So you will look at both socket-based code and RPC code in that lablet that we are going to give out as part of problem set 1. So you will see how all of this works. But let me explain some more details of how this is going. So here is essentially the timing diagram of what is happening between the client and the server. Okay? X-axis is time. Dark means executing. Dotted means waiting. Okay? The client first executes. Okay? Maybe in this case, it decides to call the add function. Okay? That add function is going to trigger a message that goes from the client and the server, handled by the RPC runtime. Okay? And then the client will block. Okay? Just as when a function is called, okay, the caller will block and wait for the function to return. That's how execution of a function takes. This is the same way. Okay? You call a function, whether it's local or remote, you have to wait for it to return. So you're going to just block, wait for the result. So this message is going to go over a network, execute, that function reply comes back, and then you get your return value. Client continues execution. Yes, question. Okay, what if the reply from the server gets lost? In about 2 or 3 slides, we'll talk about all kinds of problems that might occur. Okay, replies get lost, server crashes, client crashes. What do we do? Okay, that's something we'll talk about. Just wait for maybe 2 or so slides. Okay, is this clear? Okay, so those are RPC semantics. Okay, and just to give you some more details of what might work in local procedure calls, how remote procedure calls work. So this is an example of a conventional procedure calls. How do procedure calls work or functions work? When you call a function, you are going to put all of its argument on the stack. Okay, so you push the arguments on the stack, then you go to the code for the function, you execute, you take the arguments from there, you execute, then you maybe put the return address on the stack, you return, and so on. So you are using the stack in the program, which is a piece of memory, to send arguments back and forth. This is, remember, I called this unstructured communication. Okay? In this case, it's just communication, really not communication in that it's not inter-process communication. This is just communication between 2 functions of the same process. Okay? But you are going to use a stack to call these functions and so on. Okay? When you call remote procedures, there is no using the stack. Okay? Because if you just say, I'll push arguments on the stack and I'm going to send a message to the other end, that other end has no access to your process memory. This is a process running on some other machine. So you can't get the arguments from the stack of the calling process. You have to send the argument as part of the message itself, okay? Which is what you saw. Right? So if you look at what I showed you, you'll see that the arguments are actually sent to the process, because you can't just push them on the stack like you are doing for local procedure calls. Okay? That's one issue. Okay? But that's not the main issue. Main issue is what happens when you have certain types of parameter invocation. So if you have local procedure calls, you can, if you probably know how all of these work, you can do what is called call by value or call by reference. Okay? When you have call by value, make a copy of the argument and you send it. When you call by reference, you essentially are passing a pointer to that function. So if the called function makes change to that argument, the changes are going to be reflected up as well. So essentially, when you are calling local functions, you can pass a pointer, which is called by reference effectively. Okay? But when you call a remote procedure, you cannot pass pointers. Okay? Why not? Sorry? Not shared. What is a pointer? Pointer is a memory address. Okay? Because that's how you call by reference. You say, here's the address of the argument I'm passing. So you say, here's memory address 10. If you pass memory address 10 to another machine, if we try to dereference the pointer, it will look at address 10 on that process, not on the original process, because there's no way to come back and look for the memory contents of the call process. Okay? So essentially, pointer passing is prohibited when you call remote procedure. Okay? This is the first difference between RPCs and local procedure calls. There is no call by reference. Only call by value. You pass everything in the message, you get it back. Okay? So you cannot actually do call by reference, simply because you cannot dereference pointers across machines and so on. In the normal case, there are advanced systems that do that, but by and large, if you take any RPC system, it will disallow or not allow, as in it doesn't even support call by reference. Okay, that's the first problem. Second problem, global variables are not going to be allowed either. With a global variable in process A is not accessible in some other process on some other machine. Right? So when you're local procedures, you can make global variables, you can do whatever you want, and all of that memory is accessible because all the code resides in the same process. Okay? When your code is split between processes, you can't do global variables. That's also disallowed. When you can have global variables, but you just can't refer to it from another process. Okay, so your remote procedures better not access global variables, because that will not make sense. You cannot also assume call by references. Okay, so that's another problem. The other thing is, if you are going to pass complex data structures, okay, you have to decide how are you going to send it over the network. How is that data structure reconstructed at the other end? Let's say you pass a two-dimensional array. Okay? Both parties better agree whether you are sending row by row or column by column. So if you send row by row and you reconstruct it as column by column, your message, your matrix has got transposed. That's not what you want. So you've got to agree, how are you sending complex data structures? How are you going to reconstruct them? So that's a protocol that the RPC runtime system will have to agree on. Okay? So that all this message passing makes sense at the other end. Okay? But that's not the only problem. There are many other issues. Okay? One more issue is called marshalling of arguments. So marshalling of arguments is essentially a set of rules that both the sender and the receiver have agreed on, where they say this is how we send complex data structures and this is how we reconstruct them on the other end. Okay? So you'll say, here's how I'll send a two-dimensional array, here's how I'll send a list or any other data structure. Okay? But there's another more important part here, which is how do you ensure that this works across platform and hardware? Okay? Because nowhere have we assumed that the client and the server are going to run on the same type of machine. One might run on Mac, the other might run on Windows. Mac might be an ARM architecture, Windows might be Intel architecture. Okay? More importantly, one could be a 32-bit machine, something else could be a 64-bit machine. One could be a little Indian architecture, the other could be a big Indian architecture. Okay? So you need to know how to bridge these hardware differences, because you can't assume that your client and the server will run on the same machine. Client could be on a phone, server could be a big machine. You have not made any assumptions how socket communication works, how RPCs work. They're designed to work over different operating systems, different hardware platforms, and so on. Okay? So you need, as part of marshalling and demarshalling of argument, yet another set of rules that enforce hardware independence. This better work across hardware platforms. Should not say you should only go from Linux to Linux or Mac to Mac. That will vastly limit how you deploy your distributed application. Okay? So simplest example is maybe the sender is little Indian, the receiver is big Indian. Little Indian and big Indian means if you have an integer, which is the most significant and which is the least significant bit, one reads left to right, the other reads right to left. Okay? So if you have two hardware architectures that don't match, if you send one integer 10, let's say you send 10 over to the other end, if you read it backwards, it will look like 1 million. Okay? Because your one is in a different spot there. Okay? So if you don't account for these hardware differences, any simple things like even sending integers are not going to work across hardware. Okay? So as part of marshalling and demarshalling, you will construct rules. The rules might say, when I send something out, I always send it as little Indian, regardless of my native architecture. Okay? So my native architecture is big Indian, I'm going to flip the bits, send it out, and at the other end, you know that everything is coming as little Indian, so I can retranslate it back. Okay? So you have to do all of these things underneath for this RPC system to work. Okay? But the good thing is you as a programmer don't deal with it. This is what our RPC system designer would have to deal with. The person who's writing the RPC system and the libraries has to deal with all of these issues. Okay? How do you send arguments? And of course, we haven't even gotten to how are you going to locate the server and things like that. Yes, question? Yes, this is exact question is it analogous to serialization? The Java world is exactly serialization. Okay, so that's one way by which you can do exactly that. But of course, RPC is predated Java and serialization, so they called it marshalling. But when you get to RMI, which we'll talk about next time, that's RPCs in the Java world, you'll essentially use serialize, deserialize. Okay, the system will do it for you, but that's what you do. Any other questions? Okay. All right. So here are some steps which I'm not really going to go into. I already talked about this. The one thing I did want to mention but forgot is the part of the application. Okay, so the way you go back several slides here. Okay, the way you will write an RPC program is you will essentially write the code for your function and invocation, but then you'll also have some definition of these functions that are remote procedures. You have to declare which functions are local functions, which are remote, because the system doesn't know what type of. So as a programmer, you will say these are remote functions, these are not, and then you will actually invoke a special type of a compiler that's called an RPC compiler. The RPC compiler is going to look at the list of remote functions that you have specified and auto-generate some code for you. That code is called stub code. Okay? That's the code that's actually going to construct the message, send it back, and so on. Okay? And you will take that code and your code, and you will compile it together to get the actual binary for the application. Okay? So there's some auto-generated code that the RPC system generates for you based on what code you're trying to write. Okay? That is often called stub code. So you will see that there's a horizontal line in the client and the server process. The assumption is all the code at the top is the code you write as a program. Or the code at the bottom is the code that the compiler writes for. This is a special compiler. It generates some stub code, and then you use an actual compiler to construct the binary. Okay? So the stub code is always auto-generated. And you will see that when you write your, not write, but try to play with this lablet, you'll see some code that's auto-generated. Okay? So, so that's with that background. So let's go back to the steps. So the steps is client procedure is going to invoke a remote procedure. That remote procedure will go to the stub code. The stub code will build the message called the OS. The OS will essentially, client OS will send the message to the remote OS. The remote OS will get the message, process it, and then the response goes back. Okay? What is not shown here are all the TCP/IP steps, which are also happening in the background. Okay? For the client OS to send a message to the remote OS, it actually has to set up a TCP connection, of course. That is done using the socket method that we have talked about, but done by the library for you. Okay? So marshalling and demarshalling of arguments, I already mentioned a lot of this. So the standard solution is convert everything to a well-known representation called an external data representation, or XDR, to deal with hardware differences, to deal with 32-bit, 64-bit. So everything is self-described, saying here's an integer, 32, 64-bit. Okay, it's always going to go out as big Indian or whatever the XDR representation says. So then you can then know what is coming and how to reconstruct the data structure. Okay? And then if it's, as I said, just as you do Java serialize, marshalling will decide what are the rules by which you send complex data structures. You will prohibit pointers, okay, and so on. Okay, so as I said, it's called serialization in Java. We'll look at that again next time. Okay, so this I already mentioned. I will not talk about this again. Okay? But let's not talk about this problem of how, when you invoke this function call, which is a remote procedure, how is the runtime system going to find the server? Because as a programmer, you didn't specify an IP address. You didn't specify a port number or anything like that. Okay? So there are several different ways to do it. Okay? One is, of course, there are some RPC system that allows you to, before you call the remote procedure, to allow you to specify the server name, its IP address, and the port number. If you hard code it, then there is no problem. The client stub knows whom to contact because the programmer specified that explicitly. But most RPC systems are not going to ask you to do that necessarily. Okay? So what you can do in that case is you are essentially going to use what is called a directory service. When the server starts up, when the server code starts up, it's going to register with a special service. Say, I am a server that provides this service. Here are the functions I'm exporting. Okay? So we'll register that with the directory service. When the client needs to locate the server, it will ask the directory service, is there a server that implements the add function, for example? Okay? And then you can do a lookup and say, yes, there is a function, there's a process that provides the add service. It's running on this machine at this port number. So that's the machine you want to call. Okay? So you can always use a directory service and get around this problem of having to hard code IP addresses and port numbers. But this is going to require the server process to always register with a directory service, and there has to be a directory service running somewhere on your machines. Okay? And then the client machine has to first connect to this directory service to locate the server. Okay? So these are two ways you can actually handle this. One is you can, of course, hard code, but that's not recommended. The other is to actually go and locate the service, which is called bindings, by the way. So that's called binding the server to a specific address. Okay, that's a good question. So you can say, what is the same function is present in multiple? What if the same two programs use the same server name? Because you also have to pick a name of a service. Okay, so you could have this collision. So what you will do is you do want to make sure that the name is unique. So if you try to register it and find it registered, it may actually give you an error. So you might have to pick some name or add some version number or something that makes sure there is no collision. Okay? Not for the function name, but the service name has to be unique. Because then you can have different functions in that service. That's okay. Okay? All right. So I have only 1 minute. I'm not going to go into this today. We'll come back to this. So this slide is basically talking about what happens when there are failures. Okay? So something that we never worry about when you write local procedures. Local procedure, you call a function, it returns. If you have a bug in the function, okay, the process crashes. There's nothing you have to worry about. Okay, the code is not going to run. Of course, you have to worry about debugging the code, but you don't have to worry about dealing with it at runtime. Okay, either your function executes successfully, or there's a bug and you might have an exception or something like that. It'll either crash or you have to do exception handling. This gets more complicated because all kinds of things can go wrong when you are invoking a remote procedure. Okay? The client may not find the server. Server may have not even started. Okay? So then you are going to just have to return an error saying this add function cannot execute because there's no server that implements that. Okay? That's one problem. Okay? Or you are essentially either the request going from the client to the server may get lost or the reply may get lost. Okay? So you may call the add function, no message comes back. So you're just waiting forever, waiting for the add function to return, but nothing comes back because the network just lost your message. Okay? So what do? You wait forever. Okay? So you might have timeout mechanism saying, okay, I wait for some time. If it doesn't work, I resend a message to that service. Okay? So that's one approach. Okay? Now this requires that you have to make the operation what is called idempotent, which means that multiple executions of that function should result in the same end behavior. Okay? So if the server process has state and your function is modifying state, then making multiple requests of the same function because of lost messages can cause a problem. Okay? Here's a very simple example. Okay? Let's say the server process is a bank database. Okay? Okay? The client process is saying, let me deposit $100 to my bank account. So you send a message saying, add 100 to this bank balance. Okay? So let's say the message goes and it executes successfully, but the reply gets lost. You never hear back saying, yes, success or it's done. Okay? So you time out and you said, add $100 to this bank balance. Okay? That message goes again. And if it executes twice, your bank balance is incorrect. You as a user is happy, got more money. Bank is not happy, right? So you don't want this to happen. Okay? So idempotency will say that even if you execute that same function multiple times, the end result should be the same. Okay? Now that's not easy to implement because the runtime system has to track whether this client has already sent this message before. Have I executed it? If I executed it, I don't execute, but I just cache the reply and resend the reply. So you have to do all kinds of extra work for idempotency, not something that you wouldn't normally worry about. But in this case, because failures can occur, you got to worry about. Okay? Next time, we'll see some techniques that allow us to deal with some of these problems. We ran out of time today, so we'll stop here.